Okay, our next speaker is going to be Arvind Shekar, who's local in Southampton. How does this work?
Welcome everyone to my talk, and I'm really happy to see a lot of you decided to come to my talk. So I'll be talking about some work that I'm doing with Professor Monica Taylor here at Southampton. So the brief outline of my talk will be as follows. I'll be discussing this measure called entanglement entropy, which you guys have seen a lot in this conference, and I'll motivate why we have to study this measure and how to calculate this measure in higher dimensional spacetimes. And then we'll see what relevance it has in black hole evaporation process. So whenever we have some ignorance in a system, we can associate a Shannon entropy with respect to it. And in quantum mechanical system, this ignorance is captured by the density matrix, and we have the von Neumann entropy. But why is this measure useful to us? So let us quickly recap that quantum mechanics has non-local correlations. So what that means is you cannot always factorize a state as tensor product states. So if I consider one such general pure state, so I can always write a state using the Schmidt decomposition in this form. And if I trace out the degrees of freedom with respect to one of the subsystems, then what I end up is with a mixed state. So I started with an entangled pure state and ended up with a mixed state. And if I start with an unentangled state, then this is going to be pure again. So in a sense, the degree of mixedness captures the degree of entanglement. So it will be nice to have some measure to quantify this, and that is exactly what the Shannon entropy does for us. So by calculating the Shannon entropy of the subsystem, one can see how entangled the mean system is. And since there is a trace involved here, this is also invariant under unitary transformations. This has a wide range of applications. For example, if you want to know the optimal number of bits to encode data, then that is given by the Shannon entropy. So it quantifies information. It quantifies correlation. So if you take a quantum field theory system, then usually when you have an uncorrelated system, the entropy of the joint system is equal to the sum of the entropies. But then usually the entropy is less than the sum of the entropies when you have a correlated system. So in a way, the difference, which is the mutual information, quantifies correlation. One can, of course, alternatively also calculate the two-point functions. And even if you have a mixed system, if the entropy of the joint state is less than the entropy of the individual state, then that signals entanglement. So this is usually not true at all in classical mechanical systems. And of course, in condensed matter, in many body systems, when you have a finite dimensional Hilbert space, you can probe thermalization, where you have a linear growth with time for entanglement entropy. And in phase transitions, you have a conformal field theory, and the entanglement entropy depends on the central charge and has a logarithmic growth with respect to the size of the system. So you can use entanglement entropy. And of course, our favorite setup, holography. So can we somehow holographically calculate this measure? So of course, so you can calculate the minimal area that goes into the bulk and shapes the boundary with the subregion you're interested in for field theory. And this remarkably calculates the field theory entanglement entropy. But our focus will be on black hole evaporation. So we know that the black hole entropy goes as the area. So as the black hole evaporates, it loses mass and its area reduces, so the entropy reduces. But then the entropy of the outgoing radiation increases, and since it's in a mixed state, the entropy keeps on increasing, and at some point there's not enough degrees of freedom to entangle and purify the black hole state. So one can actually go from a pure state to a mixed state in the evaporation process. And we know that entropy is invariant under unitary evolution, and the entropy of a pure state is equal to 0. So we have a non-unitary evolution. So Don Page showed that if you need to have unitary evolution, then one has to go from a pure state to a pure state, and one has to follow a curve that looks something like this. So that is the goal. So recently, people proposed quantum corrections to the field theory entanglement entropy. So instead of calculating just the area, instead of minimizing the area, we minimize both the area and also the quantum field theory entropy. And that gives a new candidate surface, which is called the quantum extremal surface. And that is what one needs to consider. So if this quantum extremal surface is at a finite point, then you have a finite subregion. And if you are starting with a pure state, then the entropy of this subregion is equal to the entropy of the complementary regions. And then you have a region that is disconnected from the asymptotic boundaries, so which people usually call islands. And the correlation between the islands and the region that is connected with the asymptotic boundary actually purifies the state and you recover unitarity. So this is remarkable that we can achieve this in a semi-classical setup, and this actually recovers the page curve and unitarity. So the presence of islands turned out to be crucial. So we started with asking the question, when exactly are there islands in higher dimensions? So for that we need entanglement entropy on a static background. So let us see what are the conditions to have islands. So let me start with a static black hole and consider a subregion R going between R1 and R2, spanning theta and phi on a constant time slice. Then minimizing the generalized entropy means certain conditions on the first derivative of the generalized entropy. And if we need the minima, we also have conditions on the second derivative of the generalized entropy. The quantum field theory entropy over here has all the information of the QFT sitting inside it, and this is purely a geometric quantity. So these are conditions on the quantum field theory spectrum in terms of the geometry of the space-time we are interested in. But then calculating this quantity is actually really tough, and there's a huge gap in literature. So for example, we only know results in 1 plus 1 dimensional CFTs for vacuum.
Can I ask you a question about why is the second inequality correct? I mean, I thought that the sum, we want the sum of SQFT and the sum S area, that's the second derivative of that to be non-negative.
You need a minimum, right?
Yeah, the minimum of the sum.
Yes. So if you need a minimum, then you have SQFT plus S area. The second derivative has to be greater than 0, right?
Question one.
Probably is a type on the slides.
Let's maybe keep the questions for
Yeah,
because he's a bit
maybe
tight.
Yeah, so there's a huge gap in literature. So we only know results in 1 plus 1 dimensional CFTs, and there are some results in 2 plus 1 dimensional CFTs for vacuum, and usually on flat space. And we also know certain universal features, and well, of course, we can go and calculate entanglement entropy using the RT prescription, but then usually in higher dimensions, the RT surface is described by a nonlinear differential equation, and it's usually difficult to solve, and we only can do numerics. But the saving grace for us is the replica trick. So what is this? So instead of calculating the logarithm of a infinite dimensional density matrix, you can calculate the trace of q parts of the density matrix, which is a number, and then take the logarithm. And then when you take the q tends to 1 limit of this, you recover the von Neumann entropy. So have we really simplified the problem? No, we have just created difficulties, because what is trace rho bar q? So this trace rho bar q is the partition function on a slightly complicated manifold, where you take the subregion you are interested in and make cuts, and you identify the top cut with the bottom cut cyclically as follows. So we need the partition function on this, and we need the logarithm of that, which gives the connected generating functionals on the replica and q copies of the base manifold. And we need the order q minus 1 piece of that. So we are not really interested in the entanglement entropy itself, but the scaling behavior of the entanglement entropy, because that is what plays a role in probing islands. So if I change the subregion's length, what happens to the entanglement entropy? So the only scale that we have here is the length of the entangling region. And scaling that is the same as scaling the energy scale in the opposite sense. And if we consider CFTs, we can ignore the one-point functions, and because the beta functions go to 0. Then we only have variations with respect to the metric of the connected generating functionals on the replica and base manifold, and the variations of the metric itself in the scaling of the entangling region. So this part gives the stress tensor one-point functions on the corresponding manifolds, and then we have a scaling of the metric itself. So we know the quantities on the base manifold, but what are these quantities on the replica manifold? So let us try to understand that. So if we look at the replica boundary conditions, in the bulk of the entangling region, you recover the same manifold, but when you focus on the boundary, you get a scenario that looks something like this. So if you identify the cuts cyclically, then you get a cone, and this cone has an opening angle of 2 pi q. So we have a conical singularity. So I've used the coordinates rho, which is the distance from the conical singularity, and psi, which is the angle 2 pi q that quantifies the cone. And we can consider only the metric around the tip of the cone, since that captures the conical singularity. And one can regulate this cone by introducing appropriate functions that have certain properties. So it is actually enough to consider the metric around the tip of the cone, because the metric remains invariant everywhere. What about the replica stress tensor? Now that we know the metric, we can also calculate that. But before going to that, let us look at the difference between the connected generating functionals. This actually ends up picking quantities that are coming only from the conical singularities. So it is actually useful to consider a q-1 expansion of the metric and the stress tensor. And you just notice the notation that T mu nu1 is the order q-1 piece of the replica stress tensor. So how do we calculate this? We can use conservation and trace equations now that we know what the replica metric is. And the trace equation is true when you have CFTs. The trace has to be equal to the anomalies. So this gives us d+1 equations, which completely determine the order q-1 piece in terms of the stress tensor 1-point function on the base manifold. So there a lot of cancellations happen when you calculate the difference, and ultimately what you get is the scaling of the metric on the base manifold and the order q-1 stress tensor 1-point functions, which is completely determined by the 1-point functions on the base manifold using the conservation and the trace equations. So as a proof of principle, we have also calculated this for vacuum and thermal states with a planar boundary in flat space. So for a vacuum state, the stress tensor 1-point functions, the replica stress tensor 1-point functions, depends on the distance from the conical singularity, and goes as this, 1 by rho pi d. And the scaling of the entanglement entropy for a region of length delta x goes as 1 by delta x to the power d minus 2. And when you have a thermal state, you also have a pressure term that goes as p times delta x squared. So you can also go and calculate this for more complicated setups. Well, the initial question that we started is, when are there islands? So we can take the result that we just obtained, and we can see if there's a QS, and there indeed is a QS, surprisingly, even in flat space for thermal states. And even when you consider like spherical boundaries where anomalies are involved, you again get a candidate QS. So it seems like whenever there's a dimensionful quantity or anomalies involved, you end up getting a candidate quantum extremal surface. And since the scaling is dependent on the stress tensor 1-point function, this introduces certain constraints on the stress tensor 1-point functions when you demand islands. So of course, one can go ahead and calculate this for more general setups. We have just done an explicit calculation for flat space. You can go ahead and do it for static spacetimes and more complicated states. One can consider stationary spacetimes. Over there, the conservation and the trace equations will be appropriately modified. And because we do not have spherical symmetry, one needs to also consider finite entangling regions in the theta and phi directions as well. And that might show up more dynamics. One can consider spacetimes with no time cancellation symmetry. There was a nice talk by Michael Heller where he spoke about time-like entanglement entropy. So one can use the replica trick and the machinery that we have set up to calculate a replica approach for this time-like entanglement entropy. And we saw a huge interest in Carolean and celestial CFTs in yesterday's talks. So one can also calculate entanglement entropy using the replica trick in such setups. Over there, of course, this stress tensor conservation and trace equations are modified because we have a degenerate metric and direction. So do we have a holographic proposal for that? And of course, the main idea that we have been going up against. So when are there really islands? What are the explicit constraints? And what interpretation does this have on the dual CFT side? Thank you.
Okay, have some minutes for questions. Yeah. No, this time for the recording.
Just could you elaborate on your last point on this split?
About this?
Yeah. What's the relevance of the QSC to this?
So,
What's the relevance of the quantum focusing conjecture to what you're describing?
so we had explicit calculation of the QFT entropy, right? And the quantum focusing conjecture is about how the generalized entropy varies for null congruences. So one can see if there are better bounds that one can get by calculating these quantities directly. So that's what I mean.
Just so checks a bit.
Checks, yeah.
Any others? I have just a curiosity about time life and entanglement entropy.
Yeah.
This is a new concept for me. I don't understand what it means in the quantum information sense to have an imaginary entanglement entropy. Is there a way to understand this?
I mean, the way I see it is you basically have entanglement between different times. You take different time slices and you have different states. You have unitary evolution, and then you can have entanglement among them, and somehow this captures that is what I understand. But I have not completely explored it either, so yeah.
The timing is usually like between states on the same Hilbert space, and these are not in the same Hilbert space. And it's not.
Okay, so let's maybe try Arvind again.